Alright. Oh my god, my audio is really loud. Are you guys ready? Okay, we're just about to get started. Please let me know if the audio is broken. Hello everybody! Speeding at Seeds, me Z. Hello! Oh my god, well first of all, thank you so much to Dr. Toto Hex for the raid, even before I got started. Can everybody hear me alright? Hopefully the background music isn't too loud. Let me just quickly check that everything is alright. Yeah. Okay, I think that should be good. Is everybody ready? First off, thank you all so much for joining. Loud and clear? Okay, great. Hello everybody. Well, how about we do attendance first, because we have many new Orbeez who joined the channel, plus we have some few special guests as part of the STEM VTuber Symposium that I'd love to showcase. So, first things first, I want to first show a little bit of information about the STEM showcase. Thank you so much. Oh no. Everything is scuffed. Thank you so much to whoever just subscribed. I didn't see that. I'm so sorry. Hi. So this is part of the 3rd annual STEMTuber Symposium, and I'm so honored to be part of this incredible community of passionate STEM VTubers who are working to share more knowledge about STEM and are using VTubing as a platform to do so. So first, let me do a quick attendance. Hello Giancarlo, hello Mr. E, hello Stella Curie, hello Xenotime, hello Dr. Ekelus. For context, Dr. Ekelus was the one who reached out to me to be a part of this symposium, so huge credit. Hello Cherry Saves the Universe, hello Dr. Toto Hex, thank you so much for the science raid. Hello Eggy Nugget. Hello Water Knight, hello Carbon. As you guys may know, Carbon and I have a collab that is happening this Saturday, so super soon, which is also going to be about science, so stay tuned for that. Hello Haymarket Riot, hello Astro Atropos, hello Architelos, hello Yansho, hello Stella Curie, hello Galileo, hello Water Knight, hello Astrakara, hello Rain, hello Paul, hello everybody who just joined. Thank you all so much for being a part of this stream. So for those of you who came here through the raid, I can do a little bit of a brief introduction. Hi, I'm Z. My full name is Syzygy Altair, which is actually the combination of 2 epic space words. I do physics VTubing content. I also kind of play around with engineering and aerospace. I'd say my specialty is in astrophysics, so this is why I'm doing a talk today on exoplanets, which was highly requested by several Orbeez, and I'm so excited to share this slideshow that I've been working on for quite a long time. I said hi to Stella Curie twice in your panic. Yes, well, this is a great audience that we have here. But before we get started, I do have a couple of announcements. First, check out the STEM Symposium. I believe I've linked everybody's channel information down below. If you want to check out their channels, if you want to see their live streams, there's going to be a whole bunch of topics across physics, across psychology, and more. So definitely please check it out. In addition, I just wanted to thank you all so much for 1.7k subscribers. We have so many new Orbeez because one of my posts on Reddit kind of went viral. It was about me being a galaxy researcher and a VTuber at the same time. So if you came from that, hello, welcome. So glad you were able to catch me live. And I hope you stick around. In addition, one more announcement before we get started. I don't want to bog you guys down too much with announcements. I'm trying to find... I am struggling to find my image. I was just going to announce... Yes, there we go. Oh, thank you for all the emojis. This stream is not only part of the STEMTuber Symposium, but it is also part of a 2-week program that I have for myself to participate in ZEDUCATION. In fact, all of you guys will be ZEDUcated by the next 2 weeks. That's because we have so many cool things lined up. We have today the Exoplanets live lecture, which is for the STEMTuber Symposium. This Saturday, I am also doing a collaboration with Carbon on space environmental testing, which both of us, hint hint, have a lot of exposure to IRL. So I really want to share this with you guys. We're both physics people, so time to put that big brain knowledge to use. We're gonna ask questions like, why do we need to like vibrate satellites before they go into space? How do we make spacecraft radiation safe? And more. Then the following week, I am planning, I don't know if this will be on Monday just yet, but I'm planning to read some lay-friendly articles with you guys on some of the most exciting recent astrophysics discoveries. And then that following Saturday, I'm going to be collaborating with my V-Theorem genmate, Nep, who is a horticulturalist. And it'll be a Q&A style where we'll learn more about plants. We had a bit of preview of this during my charity stream where we were talking about how horticulture has affected the LA wildfires as we were raising awareness for LA wildfire relief. So this will be sort of a continuation on that, and will be an opportunity for you guys to ask questions on plants and gardening. So yes, yippee, finally a professional doing these and not some TikTok rando. Yeah, no, exactly. I mean, one of the goals for my channel and for all of the STEM tubers involved in this symposium is to help provide you guys with direct scientific knowledge so you guys can learn a lot more in a way that is, I guess, more accessible, because, I mean, it's just more fun to learn about nerdy topics from an anime girl VTuber, right? I can't wait for my brain to wrinkle. Yes, actually, by the end of this, your brain will look like that photo of me in that top left corner. Science research is so important, but science communication is underrated. No, exactly. That was one of the reasons why I started this channel, to be more involved in science communication, and I'm so glad that you guys are also part of this journey. That's why I'm here. Oh, I'm so glad that you guys have so many sweet words. We need to get the information out there. Exactly. So this, I don't want to yap too much, but this is the upcoming schedule. Please join. And yeah. So I'm gonna put this into the corner, and I do not want to take any more time because I want to get started. I want to talk about exoplanets. Exoplanets are super cool. And okay, one last thing, I promise. One last thing, I promise. If you have any questions, whatsoever, please put them into the Google form that I've linked in the pinned comment. And I will go through all of the questions at the end of the talk, and maybe even get a chance to have some of the science VTubers join us on this stream. All right, how does that sound? Yes. The stereotype is that scientists are emotionless and cold when they're actually fun and caring people. Yeah, no, I mean, I think I'm pretty fun and caring. Orbeez, what do you guys think? Do you guys think I'm fun and caring? I don't think I'm very mean. Okay, let's get started. Whew. Are you guys ready? Are you guys ready to learn? Learn about exoplanets? Okay, because I sure am. Let me take a sip of water first. Let's go. Yeah. Yes. All right. Let's make sure this is not too scuffed. Okay. So, what's the goal here? Here, let me... Okay. So what's the goal here? The goal is for us to learn about exoplanets, including their types, how we search for them, and their habitability. Here, I'm gonna adjust the music so it's a little bit quieter. Yeah, So we're going to be covering a lot of different topics. So your job. Now, just because we're in a live stream doesn't mean you guys have to be active students. You guys have to be good students, okay? Good Orbeez. Your job is to ask the questions in the chat. And I want to make this as accessible as possible. If there is a question that you have, feel free to use the Q&A form. It can be anonymous. And I promise you, no question is a dumb question. There have been so many instances where I felt nervous to ask a question, and people in the room, people in the talk, had the same exact question that I did. So please do not be afraid to ask questions, and I'm also happy to clarify anything if needed. So yeah, hype. I've never heard the term exoplanets before. Well, actually, that's a perfect transition because we're going to be talking about what are exoplanets. We're also going to be discussing what types of exoplanets exist, how do we find exoplanets, how do we identify habitable exoplanets that could potentially host life, what future missions will study exoplanets, and what have we found from the James Webb Space Telescope. So this is a lot, but let's go through things one at a time. So tell us, Z, what are exoplanets? Yes, what are exoplanets? To put it simply, exoplanets are planets outside of our solar system. And so as you can see here in the background, there are so many different types, including ones that sort of look like Jupiter's, ones that have rings, these incredibly tiny rocky looking ones, and we'll go into detail about their specific types. So a little bit of backstory. Long before we even discovered the first exoplanet, there were ancient thinkers like this guy named Giordano Bruno in the 16th century who suggested that stars might have their own planets. Now, at the time, everybody thought this guy was crazy. By the 20th century, advances in astronomy started to hint that other planetary systems could be common and that our solar system isn't special and that it isn't at the center of the universe and so forth. And yes, Astrokar is right. This is a photo of 51 Pegasi b. In 1992, astronomers made the groundbreaking discovery of the first confirmed exoplanet, and it was orbiting a pulsar named PSR B1257 plus 12. I know, it's a very beautiful name. I would probably want to name it something a little bit cooler than that, but that's the name of the pulsar. And what they found was 51 Pegasi b, which was a gas giant. And in 2019, the two guys that discovered this, Mayer and Ekelus, shared the Nobel Prize in Physics after they found this exoplanet at La Silla Observatory in Chile. Now, fast forward to today, and we have identified over 5,500 confirmed exoplanets. And this is a plot showing how over time the number of exoplanets has increased exponentially. And the different colors represent the different methods that we found these exoplanets. Now, we have only 5,500 confirmed exoplanets, but note that there are also thousands more that are awaiting confirmation. And we found this through a variety of methods, and we found so many different exoplanets. Yeah, that's what it's all about. Yeah. And so this diversity of these distant planets is reshaping what we think about of the universe. Originally, we thought, okay, maybe the solar system is the only system out there with planets. Now we know that there are so many more. So what types of exoplanets exist? Well, there's a lot of them. There are so many different types of exoplanets. And there's not just one way to categorize them. So if you go to the Wikipedia page on the list of planet types, let me see if I can include that here. Oops. Basically, there are so many different list of planet types. There are so many ways that we can classify and categorize exoplanets. But I'm going to go into some of the main types that scientists have identified and studied. So, we have hot Jupiters, super Earths, mini Neptunes, and rogue planets. And I'll go a little bit into more of those. So the first one is hot Jupiters. So initially, the exoplanets that we knew about the most were the biggest ones because they were easier to spot. And not only were they the biggest ones, but they orbited very close to their parent stars. And that's because the method that they used to discover this relied on something known as the transit method, which I'll go more in depth into later. It's this idea that when you have a star and the planet passes in front of it, the brightness of the system as a whole appears to decrease. So bigger planets and planets that were closer to their star would end up being like a bigger eclipse. And so it would dim the star a lot more. And that's why these first planets were called hot Jupiters, because they're giant planets, sometimes even more massive than Jupiter, but they can orbit their star closer than Mercury. So we don't have any hot Jupiters in the solar system. Now, of course, this was incredible to astronomers because a lot of these theories of planetary formation had indicated that giant planets like our solar system should only form at large distances from the stars. But as we found more planets of different varieties, we're actually seeing that these hot Jupiters, although they were the most type of exoplanets that we found at the start, now only make up the minority of exoplanets. So what other types of exoplanets are out there? Yeah, no, it's amazing, right? Yeah, no, these are completely new that we couldn't have envisioned in our solar system. And to answer the quick question from Dr. Toto Hex, are hot Jupiters still gaseous? I thought that the closer planets would be solid. Yeah, but these hot Jupiters have a lot of energy. In addition, they are mostly made of gas. There are also different types where they're made up of solids. But in general, they are made up of gaseous material. In some cases, they can also like rain solid material. There are so many different types out there. So yeah, I hope that answers your question. Yes, glory to the super Earth. So next up are rocky planets that are larger than Earth, but they're smaller than Neptune. So they're sort of like in that intermediate zone. Now, these are super cool because they have thick atmospheres or surface conditions that could support liquid water. So they make them really interesting targets when we're searching for habitable conditions. So they can be up to like twice the size of Earth and maybe even like 10 times of their mass. So the idea of super Earth, yeah, no, he is chonk. It's actually only a reference to the exoplanet's size. And so we actually don't know very much about the nature of these planets because we don't have anything like them in our solar system, but they appear to be one of the most common among the planets found in our galaxy. So next up, I think this is a little less fun than the super Earths, but these are mini Neptunes. These are planets that are a little less massive than Neptune, but they resemble Neptune in that they have these thick hydrogen-helium atmospheres, probably with deep layers of ice, rock, liquid oceans, ammonia, water, etc. So this diagram here shows sort of a comparison between a super Earth and a mini Neptune. So super Earths are mostly rocky. They are twice the diameter of Earth. Now, mini Neptunes are 2 to 4 times the diameter of Earth with a rocky core surrounded by a gas envelope. So if you can imagine, it's like Neptune, but a little bit smaller and more rock on the inside. Isn't our solar system an outlier in regards to most star systems? Like our inner planets are much smaller than average. I actually believe so. In addition, we have found systems that have a lot of planets in them, but it is quite rare to encounter systems that have as many as 8 planets like we do. Is this to scale? Yes, I believe so. Yeah. Actually, I don't know if that scale between Earth and Neptune is... I think that's actually correct. I assume that this diagram is to scale. Yeah, it's because most exoplanets are probably not detectable to us yet. A lot of the smaller ones are incredibly hard to spot, which is why it's so important to be using a wide variety of methods. And I'm going to go into how we detect exoplanets in just a second. But before we do that, the last type of planet is these rogue planets, which are really funky. They kind of just drift through space alone. Very sad. They could form through the collapse of a gas cloud, similar to how stars form, but they just are really tiny, or they're ejected from their original planetary systems by other gravitational interactions. They don't experience any warmth or light because they're not orbiting a star, and they're just there in perpetual darkness. Now, that being said, a theory that I've actually heard is that rogue planets could still host oceans. And the reason for that is because they could be kept warm by the leftover heat from their formation or from like radioactive decay. But in general, I don't really know much about rogue planets, and they're really hard to find because they don't orbit a star, they're not part of a system, they're just out there and they're incredibly tiny and hard to spot. So, that brings us to the next question. The next topic. How do we find these exoplanets? And how did we find so many? 5,500 of them and thousands more to be confirmed. Gotta drink some water first. So there's this really nice website made by NASA that goes through each of the different methods of detection. It's actually an interactive website. Let me actually paste that into the chat. So if you want to check that out, definitely please do. Here, let me paste that. It's a really cool website, but I'm basically going to go through the content of this website and sort of how each of these planets were discovered and how these methods work. So the first method that I want to talk about, which led to the discovery of about 1,000 planets, is radial velocity. So if you can see here on the animation, the GIF or GIF, however you call it, on the left, you see that the star is wobbling and there's a tiny planet that's also moving there as well. This tiny wobble of a star is caused by the gravitational pull of an orbiting planet. As the star moves towards and away from us, we then see that the light changes in wavelength. So as the star moves away from us in its wobble, it appears to be a little bit more red. And when the star moves closer to us, it appears a little bit more blue. So this is called the Doppler effect. And you may have encountered it either in like the physics classroom, or if you ever hear like an ambulance and as it's getting closer to you, it's like wheel, 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 wheel. That was such a horrible demonstration. Whoever, if anyone just joined and heard that, I promise you I'm not insane. But that's sort of how it sounds, right? It's like wheel, 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 wheel. Like as it goes closer to you, it pitches up, and then as it goes away from you, it pitches down. Yeah, no, exactly. Thunder Nugget has it right. It was a great example. Yeah. Get those wheel, wheel, wheels in the chat. Clip it. Oh no. Oh no. Anywho, but this Doppler effect method is, it's really great. And it's really great for finding massive planets that are close to their stars. Because if it's a massive planet, it has a greater gravitational effect on its star. And if it's closer to its star, it has a greater gravitational effect as well. It's sort of like Newton's laws of gravitation, right? If it's closer, it has like a bigger gravitational pull. And checking for this wobble is how we found a lot of planets. Yeah, so this is astrophysics, exactly, the wheel, wheel, wheel sound effects. Now, the next way to find exoplanets is the most widely used technique, which led to the discovery of 4,329 planets, which is like basically all of them, is this method known as transit detection. So when a planet passes in front of its star, it causes a tiny temporary dip in the star's brightness. So if you look at this animation over time, as the planet is passing in front of the star, the overall brightness of the system appears to go down. So if you can imagine, if there's like a bigger planet, that brightness dip would be even bigger. And if the planet is much closer to its star, it would, or even much further, I guess, relative to us, it would appear to be much bigger as well. And so just by measuring the size of this dip, scientists can figure out what is the size of the exoplanet, how long is its orbit, and how far away is it from the star, which, as I'll talk about later, is really important for figuring out if a planet is habitable, right? Like, because if it's way too close to the star, it's going to get absolutely fried. But this is a really common method. You can measure size this way? Yeah, you can. Because it affects the size of the dip. In addition, as you know the period, you can figure out how long the dip takes place. The transit method was created by a bunch of public transit nerds who got into astro. Actually, I wish. That would be really cool. Railway of planets. So, by monitoring these dips over time, the scientists can estimate size, orbital period, which is how long a planet's year is, how long it takes for the planet to go through one revolution, and in some cases, even atmospheric composition, if the light passes through the planet's atmosphere. So a lot of missions have been sort of focused through this method because it's so powerful, including NASA's Kepler mission and TESS missions, which is why we found so many exoplanets this way. Yeah, the transit depth gives you the radius of the planet. It's fascinating how much information you can get from these light curves. Now, this next method, there's only 82 planets, and the reason for that is because this is an incredibly challenging method, direct imaging, which is actually photographing the exoplanet. So, this involves blocking out the bright light of the star that the planet orbits. This is really important because the star is incredibly bright. It will completely wash out a planet. But if you have a specialized telescope or an instrument like a coronagraph, the way that this works is that you can block out the star, and from that shadow, you can then see what does the exoplanet look like. Now, this works best in very specific conditions, obviously. It works for large planets that are far away from their stars, because then you can see the contrast between the planet and the star, and it's less obscured by the star's brightness. So, this image here on the left is the motion of a planet that orbits Fomalhaut. I don't know if I'm saying that right. Fomalhaut. I actually never learned how to say this star's name correctly. It's actually, the planet is called Fomalhaut b, and this was actually captured using direct imaging. So if you see the little like pop out in the image, you can see like 2004, 2006, 2010, 2012. The planet is moving over time. We're literally seeing the planet as it is orbiting the star, which is incredible. Now, one of the ways that we could do this with greater precision is this idea here on the right. This shows a space telescope with an ejectable star shade. And it's a technology that will be used to block out the starlight of a star and to look at the planets that are orbiting around it. Now, this is really ambitious, but it's one of the cool things that they've thought about to use this direct imaging method. Yep. Yeah, no. And just to go back, you can figure out what gas is in the atmosphere just from the shadow. Yeah, so I'll actually talk about that a little bit more when I discuss about what James Webb has found, because it's been using this method to determine the spectra. It's basically using the light as clues to figure out what the atmospheric composition of a planet is. Yeah, how can it tell it's a planet with so many bright dots around? Well, for one, there's very specific criteria. Usually this method is best when a planet is very reflective, right? But in addition, one way that you can check is by seeing the movement of a planet over time and tracking it. Typically, stars don't really like move in the background dramatically, right? And so this actually involves like a very long process, which is why there hasn't been many exoplanets discovered using this way. Astro totally wins the coolest picture award. I mean, this is really sick. I mean, it looks like an eye too, because you're blocking out the star, and just, it's incredible how they've been able to find planets like this. Yep, so next up, 232 planets is with gravitational microlensing. Now, I'm a little bit biased. I'm a little excited about this one. I think I'm actually the most excited about this method, and I'll go a little bit in depth as to why. So this method relies on Einstein's theory of general relativity. So when a massive object, like a star or a planet, passes in front of a distant background star or scene, its gravity bends. And so when we see it, the light of the planet is actually magnified. And this lensing effect gives a very specific signature. And this technique is great because it can even detect these rogue planets drifting through space, because we can actually see them through gravitational microlensing. And so what's going on in this diagram here is basically, if there is a planet, the light from the planet is magnified because of gravitational lensing, allowing us to actually see it. I mean, this is sick. This is so sick. That's why this is probably like the method that I'm most excited for, because it's like, oh my god, like, it's so crazy that you could just do this with like light bending because of like gravitational effects, right? What do you guys think? Am I being too hyped about this method? Maybe you guys are the fans of like the transit method, or I mean, direct imaging is pretty cool too. Yeah. And so we could do gravitational lensing with the sun if we go out far enough, right? Yeah. I mean, it will be a bit hard though, because you'd have to go pretty far. The sun is incredibly bright and it blocks out a lot of the sky, and you would need like a giant sun shield for that. So this is much better for like distant exoplanets, but still, you can never be too hyped. Yeah, no, gravitational lensing is very cool in general. Now, I don't want to go too much of a tangent here, but I think it's, if you've ever seen an image of a galaxy cluster, it is one of the coolest things ever. You can see the galaxies literally being distorted as their light arrives to us. But that being said, okay, chat, class, let me know if you want to see a lecture on galaxy lensing, galaxy clusters. I mean, I know more about, I don't want to say too much about what I do IRL, but I do know a little bit more about that than I do about exoplanets. But yeah, neat stuff. I have no idea what's happening. We are going through the different methods that are being used for exoplanet discovery, and I'm nerding out about gravitational lensing because you can literally see a planet, like, you're like zooming into it like with a gravitational magnifying glass. Okay, but that's enough said about gravitational lensing. It's very hype. So, the last method, which is also quite new, and only 3 planets have been discovered this way, is involving very precise measurements of a star's position in the sky. So, if a planet is orbiting a star, and especially if it's a big planet, the tug of war between that planet and the star will cause a star to move in a tiny circle or ellipse. And as we're tracking the position of the star over time, we'll see that there's a little bit of that circular wobble. Now, this is really, 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 really hard. That's because you need a lot of precision, but with more advanced instruments, we could maybe use this method more often. Gravitational lensing live lecture, the people demand it. Okay, the people have spoken. Class has spoken. Does the back of black hole accretion disk being visible from the front count as lensing? Well, this is quite a bit of a tangent from exoplanets, but yes, because you are basically looking at the back of a black hole because of the strong gravitational effects and mass of the black hole. Okay, so that's enough about the methods. Now, this is the really exciting part and probably the reason why you're actually here in the first place. How do we identify habitable exoplanets? Do these exoplanets actually have life? I mean, like, why are we studying exoplanets anyways, right? Unless it's to find aliens. Well, I promise you there are a lot of other cool reasons to study exoplanets, including, like, data analysis, including playing around with these really cool astrophysical properties, learning more about our solar system and different systems, learning more about where we are in the universe. But, okay, how do we identify habitable exoplanets? So, first, what is a habitable exoplanet? It means a planet that could potentially sustain life. And based on our solar system, we think that life, or based on Earth, I guess, life requires liquid water, energy, nutrients, and so forth. So, you might be wondering, what makes an exoplanet habitable? The answer is, we honestly don't know. We might think that, oh, it actually depends on the distance to the star, which is whether or not it's within a specific habitable zone, or like a range from the star. We might think, okay, yeah, it needs a magnetic field, otherwise it's going to be fried by radiation. Or maybe it also needs liquid water, like Earth. Or maybe it's dependent on size, because gas giants can't really host life that we know of right now. But truthfully, we actually don't know. And that's because n is equal to 1. Our sample size is equal to 1. We have only one example where we found life, and that's Earth. Which is also why, a little bit of a tangent, which is also why it's important for us to take care of Earth, right? Yeah. Exoplanets are cool without aliens. I mean, aliens are cool, but planets don't need aliens to be cool. Yeah, no, exactly, right? But it's cool to think about, like, could there be life out there? Even if it's bacteria or any other form. And if you have submitted a question to the Google form, you might also notice there's a question about me asking you guys, do you guys think there's life in the solar system? Beyond the solar system? Or no life at all, and Earth is just special? Actually, that might be a cool poll. And when I say, is there life in the solar system, I mean excluding Earth, duh. Do you think there's life out there? I'm actually curious to see what you guys think. Yes, in the solar system, excluding Earth. Okay, I'm running out of characters, but yes, outside the solar system. And no. Here, I'm curious to see what you guys think. That would be a cool poll, yeah. Have you heard of the Miller-Urey experiment? Yes. So I guess for those of you who don't know what that is, well, I'm not really that much of like a chemist, but basically what the experiment was that I believe they put in a bunch of initial elements that could have been on Earth, when the Earth was not hospitable at all, put in a bunch of energy, and found that over time, like, I believe they found like amino acids and other components of life were starting to come together. And this was just like in a bottle that was being like heated up with some of the chemical concoction of early Earth that did not have life. I mean, I think it's a really convincing experiment to show that Earth may not be special. There's some on the space station. Okay. But still, you know. You know. Yeah. Oh, yeah. They also had sparks to simulate lightning and stuff in the early Earth. Exactly. Okay, so n is equal to 1. We only have one place that we know where life is, and that's Earth. But scientists have a few ideas as to what will constitute life, right? One of these ideas is the habitable zone. And a lot of time in exoplanet research is actually being spent on whether a planet is in its star's habitable zone. So this is a region of the star's orbit where liquid water can be sustained on the surface. So that means like pretty ideal temperatures, right? And if you can see here, like Earth is in that yellow zone. It's in the optimistic and conservative habitable zone. And on the left, you can see the different temperatures of the planets. Now, if you see along the row where Earth, Mars, Venus is, that's the temperature of the sun, which is like 5,700 degrees Kelvin. And obviously, like, Mars is on the furthest edge of the conservative habitable zone. Venus is definitely outside. It's way too hot. But, of course, we found planets that are orbiting stars that are different sizes than the sun. In particular, we have most spotted planets that are orbiting these incredibly tiny stars called red dwarfs. And as you can imagine, since they're smaller and their temperature is less high, it's actually better for them to be sort of closer to the star. Yeah. So, we are learning, though, that this habitable zone might actually not be our best metric for identifying if a planet is habitable or not. Because planets that are orbiting stars might could produce higher levels of X-ray and ultraviolet energy. And that actually ends up stripping away the atmosphere of certain exoplanets. So that could lead to a planet that's like perfectly warm, perfect temperature, but it has no air. It has no atmosphere, which would definitely not be good for life. So one example of sort of this idea of the habitable zone maybe not being the best metric is the TRAPPIST system. And so some of you guys may have actually heard of the system. It was really viral on the news when it was first discovered. And yeah. Thunder Nugget, I do see your question. I'm reading it a little bit right now. A planet around a K-type star that receives similar amount of light tide from its sun than the Earth does to the moon. Actually, so tides could actually be a good indicator. One example, of course, extreme tides from a star and being too close to a star would not be good because it would lead to a lot of radiation. But one example of where we've seen tides actually being a case for life is for the moon Europa, which orbits Jupiter. And I don't want to go too much of a tangent here, but Europa is basically being pushed, stretched, and pulled by the tides due to the strong gravitational force from Jupiter. And what that's actually doing is it's heating up the insides of Europa. And because we currently know that there is an ocean underneath Europa, almost twice the amount of the oceans of Earth, that actually could heat up the ocean, leading to more habitable conditions, similar to like the hydrothermal vents at the bottom of the oceans here on Earth. But yes, of course, Paul Stormchaser also says not as bad as Io, right? Yeah. So in the case of Europa, tides are actually a good thing. They could provide the heat, the energy for life to be sustained. But on the opposite end of that spectrum is, of course, moons like Io, which also orbits Jupiter. But because of the tides and the gravitational pull of Jupiter, it is so volcanically active, there is no way there's life there. It's just fire, lava, volcanoes. It's incredibly active, definitely not stable enough for life to develop, because life needs stability. Life needs constant conditions. So I don't want to go too much on a Europa tangent. I love Europa. But that's sort of an instance where tides could be helpful or not helpful, I guess. So yes, everybody and their mothers were excited about the TRAPPIST system. Yes. So a little bit of context for those of you who don't know. The TRAPPIST system was discovered back in 2015. They found this using a telescope in Chile. And what they found were these transit dips. So the transit method in the light of a red dwarf star about 40 light years away. So then in 2017, the Spitzer Space Telescope went back to look at the system and found that there wasn't just one, there wasn't just two, but literally 7 Earth-sized planets. Now, this was a big breakthrough, and it was really big in the news. The thing is, the TRAPPIST-1 star is tiny. It's only 9% of the mass of the sun, which means that its habitable zone is much closer than it is for like a star like the sun. In fact, this whole system could fit inside Mercury's orbit, which is crazy. So this is sort of an image showing where these planets orbit. And inside this green box are the planets that are within the habitable zone of the star. And so scientists were like, oh my god, there's not just one, there's not just two, there's literally 3 exoplanets that could potentially sustain life. These are 3 planets in the habitable zone. We figured it out. We've found life. We've solved it. So, for context, this is a really tiny system. So that red are all of the TRAPPIST-1 planets inside the orbit of Mercury. In fact, it's almost on the same scale as the Galilean moons. So the moons orbiting Jupiter. So they are really, really close to their star. That must be one very small star. Exactly. And hello, Professional Skill Issue. Thank you so much for joining. So here's the catch, right? Now, everybody was excited about this system. But the thing is, these red dwarfs are the most common stars in our universe because they're so small. But they have really intense stellar flares. So these ejections of energy, radiation out in the universe. And these could strip away the atmospheres of these exoplanets over time. So now scientists are using the James Webb Space Telescope to figure out if the TRAPPIST system or planets in general around the universe that we found have any air left, or if they're just like sad, barren rocks. So now the latest data suggests that the issue might not just be the radiation from the red dwarf, which is equally bad, but this idea of the stellar wind, which is the wind of charged particles blown from the star. So this causes these electric currents as a planet orbits around the red dwarf host star. So Earth also experiences solar flares. Earth also experiences the solar wind, both of which cause a similar heating of our atmosphere. But we have a magnetic field to protect ourselves from the radiation, and we have an atmosphere, which is really important. But here's the difference with the TRAPPIST system. The difference is that the heating that's felt by TRAPPIST-1e can be up to 100,000 times stronger than what the Earth experiences with the sun. And that's because TRAPPIST-1e moves really quickly around its star because its orbit is so small, and that motion drives these powerful currents that dissipate the atmosphere and create extreme heating. So, that doesn't really sound very good for the TRAPPIST system, but it gets even worse. So TRAPPIST-1e, the good news, is that it's believed to have a magnetic field, but it's not strong enough to protect itself from these immense winds. So, yeah, no, exactly. Yeah, very nervous. It was that strong? Yeah, no, it's incredibly strong. It's because it's orbiting so close. And so, unfortunately, exoplanets that orbit these red dwarfs or orbit close to these stars may have likely lost their atmospheres, even if they are in the habitable zone. So this is one example where the habitable zone isn't really our best metric to determining if a planet is habitable at all. So, yeah. Now, the next thing that might be a really important ingredient for life is liquid water, right? So on Earth, every organism relies on water. It's the universal solvent. It's part of all these like chemical reactions that take place inside of cells. But now scientists are thinking liquid water may not be 100% necessary for life to exist. So how do we detect the magnetic fields of these planets? That's actually a great question. I actually don't know. Here, let me actually search this up. I have to assume it has to do with the planet's mass, and whether it has some like dynamo on the inside. So, okay, I just did a quick search for this. You can find them through direct detection. Oh, well, that's only if you have a spacecraft that goes close to the planet. Here, let me look up exoplanets. That's actually great. You can actually observe the radio waves emitted from the interaction between the planet's magnetic field and its host star. Whoa, I didn't know that at all. So when the planet's magnetic field interacts with the stellar wind, they can be picked up by sensitive radio telescopes. Wow, that's actually really impressive. Now, of course, this is really hard because for the radio waves to be detectable over long distances, they need to be really, really strong. But typically, a stronger magnetic field is great because it protects the planet from radiation from its star. That is really cool. I actually didn't know that. Yeah. So, for most of them, we don't know if they have magnetic field. Yeah, no, they probably require very specific conditions because that information has to travel such a large distance. You would need an incredibly accurate telescope, exactly, or an array of radio telescopes. Yeah, learning new things. Yeah, no, I actually didn't know that. That's actually super cool that they were able to find that. But of course, that means that in most cases, we won't be able to detect whether a magnetic field is present. But it would be great to detect it for cases of extreme magnetic fields, which is probably the case that is very convincing for life, right? Yeah, no, this is super cool. Yeah, thanks for the tangent. Okay, so back to the ingredients of habitable conditions. Water might not be necessary. So one example is Titan, which is Saturn's largest moon. So it's freezing, it has lakes, it has rivers, but it's not made of water. These rivers are made up of liquid methane and ethane. And some scientists believe that it's possible that there could be some life that exists there using methane, similar to the way that we use water. So this is actually a diagram showing some of these methane lakes and sort of the icy crust, the methane ice that constitutes this moon. And one of the proposed missions to understand Titan better, which could actually help us understand like what types of systems are out there in exoplanets, is the Titan Saturn system mission, which would, this is really cool. This would take a lake lander to Titan, and it would float on top of Titan's liquid methane lake. So that's the little like cylindrical looking thing on the lake. And then there would also be a balloon that would explore the atmosphere, and then an orbiter that would be circling Titan. That would give us a lot of information. And so if we were able to imagine life requiring water, Titan could be our biggest hint. And I think it's so amazing. I don't know about you guys, but I think it's so amazing that we have so many diverse moons and planets in our system. Like, we are so fortunate to have a solar system made up of these diverse moons and planets that we could get insights to systems that are light years away just by learning more about our solar system. But it also demonstrates the importance of these scientific missions to actually take place and why they're so important. Clipped Z doing the Doppler effect. Oh no! I'll have to check that out later. Do scientists think there's a likelihood of life existing on Titan? There could be life that is dependent on methane. I think Europa is a more convincing case because it literally has liquid water oceans. I've seen theories where methane might be too complex of a molecule for life to develop. Water is like very simple. Yeah, no, exactly. Not all life may need our air or water to survive and spread. In some cases, they might not even require any of them at all. If you guys have ever looked up a tardigrade, which I'm deathly afraid of, they could just live in the vacuum of space. And they can like hibernate and like not even need like food. There's incredible crazy life on our Earth too. Enceladus is better in your opinion? Enceladus is also very convincing. But I think if we were to look at the next decade or so, Europa Clipper, which was recently launched by NASA, and we actually watched it together on stream, is headed towards Europa, the moon, in about 6 years. And by doing that, like, we can literally get data directly from the moon about, like, what is underneath its crust. What is its plumes made of? Tardigrades are so cute. Why are you afraid of tardigrades? Okay, this is a really long story. I don't want to go too much on a tangent here. But when I was very, very little, not very, very little. Okay, when I was little, there were these diagrams. I saw a picture of a tardigrade, and I freaked out. I was like, what is that? Why does it look like that? And since then, people around me who know that I'm afraid of tardigrades have been putting pictures of tardigrades to jump scare me. Oh, they're just creepy looking. See, this is why I don't study biology, right? Like, I can't look at things under a microscope. It gives me, like, the heebie-jeebies. Like, have you ever looked up, like, what an ant looks like? Like, an ant's face looks like? It's weird. It's, ugh. Lumpy little guys. They're so delightfully chubby. No. You guys can hang out with the tardigrades. I sometimes get disturbed by the fact that they could literally just be in our water. This is such a strangely specific concern. Love the Z lore. Yeah, no, this is canon. Z is afraid of tardigrades. And please do not use that against me. Please, please, Orbeez. Please be kind to me. I can relate. See? I'm not crazy. Nobody tell her about the bobbit worms. Ooh, what is that? Okay, actually, I do not want to know what that is. They are too small to cause harm. Yeah, but they look weird. They look weird. That's why I don't like them. But anywho, that's an example of, like, very extreme life. I don't like the amount of evil faces. T the tardigrade, no! 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 No. Bad class. I'm just gonna have to give you guys another homework assignment for that. Only if more Kerbal Space Program. Class, are you blackmailing me? Are you blackmailing me? Stop. People theorize that there's a serpent-like creature in the methane ocean. I mean, anything could be possible. We need more missions to go back. We need to go back and understand these systems. Why hasn't there been a tardigrade VTuber yet? Oh, thank God there isn't one. Okay, well, back on task. Okay. All this conversation about tardigrades, all this conversation about what kind of life could be out there, brings us to this next question. Like, what future missions will study exoplanets? And there's a lot. There's a lot. Please don't jump scare me. You found 2 tardigrade VTubers? Exterminate them. Exterminate them. Nuh-uh. Nuh-uh. These tardigrade VTubers, they need to leave. No, I'm just joking. Protect me. Yes, protect Z. I should never have revealed my weakness, my kryptonite. Eyelash mites, ooh. VTuber war. Yeah, no, I'll start. See, I feel like I'm the type of person that isn't really going to start any VTuber war or VTuber drama or whatever. But tardigrade VTubers. Tardigrade VTubers. Nuh-uh. Now, if those tardigrade VTubers graduate next week, thanks to me. Thanks to me. No, I'm just joking. I'm just joking. I'm just joking. Fine! No! A rip, I made a tardigrade video. No! How could you do this to me? The ultimate betrayal. Rivalry in V-Theorem itself? VTuber war in V-Theorem itself? Chat, I'm leaving V-Theorem. This tardigrade slander, or not slander, this slander towards Z, threatening with tardigrades, blackmail. It cannot be tolerated. Mylan says no. V-Theorem civil war. No, no. Don't leave me alone. Gen 1.5 Z leaves. No, no. I won't go. I promise. I promise. Please protect me though. Okay. Okay. We don't want to go on a tangent too much because we have a lot of things to cover. We love you. Don't leave us. Okay. I promise I won't leave you guys. But if you guys blackmail me with tardigrades, I might. Don't do it. Don't do it. Okay. So back on task. So this is the exoplanet mission timeline by ESA. This diagram was made in like 2018 though, so it's a little bit outdated, but the James Webb Space Telescope, which is here on the bottom, has been our most recent exoplanet telescope. It's sort of used for everything, but it's really important for exoplanets, and I'll explain why in a bit. Oh, oops, the animation's a bit broken. But I just wanted to go through a few of the different missions that have been planned. So the first one here that looks kind of like a cheese grater is Plato. It's planetary transits and oscillations of stars, to be named Plato, yes. It's a satellite made by the European Space Agency that will help put more exoplanets on the map. It's scheduled for launch in late 2026. It's going to look at around 200,000 sun-like stars. So we have 5,500 exoplanets discovered already. 200,000 additional stars to characterize them and the planets that orbit them. And they're going to be focusing on terrestrial planets in the habitable zone around sun-like stars. Plato, yeah, exactly. The next one is the Roman Space Telescope. There's this really sick animation here. And this is going to finish up like the census of exoplanets. And it's going to be using that really cool method I talked about called gravitational microlensing. And this telescope is going to be so strong that it can find exoplanets down to the mass of only a few times that of the moon. That's crazy with gravitational microlensing. And it could also include these like rogue planets with masses down to the size of Mars. So this is going to be our best exoplanet telescope yet. It's going to be insane. Then next up is Ariel, which will observe 1,000 planets around distant stars. And the reason why it's looking at much less is because it's going to do a large-scale survey of the chemistry of exoplanet atmospheres. And so the reason why there's like this little like rainbow-looking thing coming out of this hole is because it has a spectrometer, which spreads the light from the exoplanet into a spectrum, like a rainbow. And from this rainbow, we can get hints about the different chemical compositions of the gases in the planet atmospheres, which is crazy. And the way that it does that is it basically tracks the emission and the absorption of different chemical elements in the exoplanet's atmosphere. In fact, this is going to be such a strong spectrometer, and of course the database of planets is going to be so in detail, like preferably ones that are closer, that can be analyzed using spectra. It's so powerful that it can actually study the clouds and monitor their variations over time, which is insane. So these are like some of the crazy stuff. Yeah, no, I love all the excitement in the chat right now. Yeah, no, this is gonna be wild. Greek Space Telescope when? I mean, I would love for there to be more telescope. This is crazy. So this is gonna be our next generation of exoplanet studies. With that being said, well, if we focus on the present, so there's a lot of excitement in the future, but if we focus on the present, what have we found from the James Webb Space Telescope? Basically, already, a lot of super sick, epic stuff. Yeah, it's going to be lit. But it's already quite lit right now. Exoplanet weather report. Okay, it won't be that specific, but it's going to be cool. Yeah, we've actually already been able to sort of track the chemical composition, and in some cases, I don't know if we've been able to track some clouds. I think in some cases, like a very few, but that's going to be for 100 planets, which can give us so much more detail, especially for those candidates of habitable life. Okay, so next up, what have we found from the James Webb Space Telescope? Well, this is what I think is one of my favorite demonstrations of how powerful James Webb is. This is James Webb's first direct image of a planet outside the solar system. So what is this, right? They blocked out the star, similar to how I mentioned before. You have to eclipse out the star so you can see the planet. And there's a gas giant here named HIP 65426b. I know, these exoplanet names are crazy. It's 6 to 12 times the mass of Jupiter. And they were able to photograph it in different wavelengths. So as shown here. And it's very young. It's only 15 to 20 million years old. And for context, the Earth is about 4.5 billion years old. And so Webb has these coronagraphs that can block out the star, allowing us to take direct imaging. And compared to the picture that we saw before, I mean, this looks pretty in detail, right? I mean, it's not great, but it's really cool to see, like, Webb is so strong, you can literally see planets around stars. Now, another really cool example of James Webb's discovery is this planet, WASP 96b, a gas giant exoplanet, which was the first exoplanet spectrum collected by Webb, using this spectroscopy instrument which is called like NIR-ISS, near ISS. Now, these spectrums are made by comparing the starlight that is filtered through a planet's atmosphere as it moves across a star, and then comparing that to what the starlight looks like without the planet. And so each of these data points, which are these like white circles, represents the amount of the wavelength of light that is blocked by the planet and absorbed by its atmosphere. So basically what we're doing is seeing like what kind of elements is the atmosphere absorbing. And by doing that, they can actually detect and measure the amount or the abundance of these key gases in a planet's atmosphere based off of this absorption pattern, which is the location of the heights and peaks of this graph. And from this, you can also calculate the planet's temperature. So a hotter planet has taller peaks. And you can also detect, in some cases, the presence of different haze and clouds, which can be inferred from the shape of the spectrum itself. So this blue line here is the best fit model that takes into account the data, which takes in the known properties of the star, like its size, mass, and temperature, and the assumed characteristics of its atmosphere. And this is the most detailed exoplanet spectrum that has ever been collected. And what's really cool about it is, I mean, literally it says water at the top. It showed evidence of water vapor that previous spectra had only like barely hinted at. This is basically saying, yes, there is water in the atmosphere and we're sure of it, which couldn't have been possible with previous weaker telescopes. So this is super, super cool. To be fair, it's just the name of the star plus a letter. Yeah, but I think it's like, of course, for organizing data, having that kind of normalized system is great, but you know, like, what if, like, some of the planets are named after people? I want a planet named after myself. They should rename WASP 96b to Z. Z the VTuber. Actually, I think there's a way to get an exoplanet named after you. Either through purchasing it or receiving some kind of award, but it's probably just gonna be like an obscure one. Anywho, the next one here is WASP 39b, which is a hot gas exoplanet. It orbits the star closer than Mercury orbits the sun. So again, this is another spectra. The y-axis is the amount of light that's being blocked. The x-axis is the wavelength. And what this is showing here is that James Webb detected carbon dioxide and sulfur dioxide in the atmosphere of a gas giant exoplanet for the first time. Now, this doesn't really sound that exciting, right? You're like, oh, well, I mean, it's not like life is made out of that, right? No, you're wrong. The detection of, oh my God. The detection of sulfur dioxide in, this is called a hot Saturn planet, is potential evidence of photochemistry, which are these chemical reactions initiated by energy from the star's light. And the detection of carbon dioxide in this case is actually really impressive because we've found this molecule in smaller rocky planets, but never for gas giants. So it makes you wonder, like, there could potentially be life in the clouds of a gas giant, right? This is pointing to, like, potential evidence for that. So, yeah. Can't you name it if you discover it, like how we do with species? I mean, you could, but of course, a lot of these are just done by telescopes, right? It's not a specific individual. I mean, that's why there's a lot of planets that are named like Kepler 16b, Kepler like 13b, because they were all found by the Kepler Space Telescope. It's not a singular individual. These are missions, groups of people. Photochemistry is awesome. Yeah, exactly. I don't know. Maybe I can discover an exoplanet and I'll name it Z. Okay, so then this is another example I'm so sorry. This is really, really exciting. So if you're getting bored by spectra, this is the last one, I promise. So James Webb observed WASP 17b, which is a hot gas giant exoplanet, in 2023. And this was really weird because there, as you see in the spectra, there's light blocked by quartz crystals. So this was the first evidence for quartz or crystalline silica in the clouds of an exoplanet, which we see like at about like 8.5, 8.6 microns. And that shows that the silica particles are absorbing some of the starlight passing through the atmosphere. And for each wavelength, the amount of light blocked was calculated by subtracting the amount that made it through the atmosphere and so forth. So this is the same exact method that we've seen before. It's just a brand new cool discovery. This is so cool. Now, that yellow line on the bottom is what the spectra would look like if there were no quartz clouds. It looks totally different, right? So this is the first time that quartz or silicon dioxide has been identified in an exoplanet. And actually the first time that any specific cloud species has been identified in a transiting exoplanet. So it's literally clouds of quartz. Isn't that crazy? Like, that's so weird. Quartz clouds. Yeah, exactly. Sounds like a balloon's nightmare. Yeah, no, that would not be a good place to be a balloon. Yeah, I can't even picture what a quartz cloud would look like. Well, given the temperature, it would probably just look like a normal cloud, right? It wouldn't just be like a solid. Or it could. If you guys have ever watched Interstellar, one of the planets that they land up on has like these like ice clouds, and it's like frozen over, and the scientists are like walking on top of the clouds, and they think that there could be like habitable conditions underneath the clouds. So that's just one example. So yeah, so that was the last spectra, but it's really, really cool to see what James Webb has been up to. And in addition, what I actually wanted to highlight an article that I actually encountered while making this presentation. This was from the Astrobites, which I highly recommend that everybody reads. It's basically research papers being explained in a way that is more accessible, more for lay people. They take diagrams, figures, they break down a research paper. And I found this article. I was like, wow, that's sick. And then I read the paper and I was blown away. So this paper is actually open access, which means that I think I could send it. Oh, I don't know if I have the link on me, but if you search it, it's actually open access, so you can actually read it yourself. And so what this paper talked about was this. Here, let me... Okay, that worked. Phew. So this article asked, how do we know if like an exoplanet is like raining crystals? And one of the ways that they do that is you can do it using the transit method. So this is actually the transit light curve, right? So the big dip is when the planet passes in front of the star. These smaller dips actually represent when the planet passes behind the star. So all we see is just the star's light. And this can give us a heck ton of information. So these secondary eclipses are when the planet goes behind the star. And this figure, and this paper also had this figure here. And what this shows is like a phase curve, which gives us a lot of information about the atmospheres, but is incredibly important when we're talking about tidally locked planets. So this is like the moon, where one side is like always facing the star and the other side is always facing darkness. Not a really good indicator for life, but in some cases that is the case for an exoplanet. So the James Webb Space Telescope looked at this system for like 40 hours in like different wavelength bands. And they got these like transit light curves. Now, one thing that you might notice here is that one side is a little bit lower than the other. So this is the bottom figure is like zoomed in from the top figure. And in the secondary clips, you can see like one side is a bit lower than the other. That means that the planet is actually brighter before the secondary eclipse than it is afterwards, which means like the hottest point on the planet has like shifted a little bit. So how can we use this information, right? Like, oh yeah, that's so cool. Well, it has to do with this idea of general circulation models. And before I continue, thank you, Eternal Sonata, for stopping by. Actually, I believe they were the one to suggest this topic, so thank you so much for the suggestion. No, Astrobytes is great. Astrobytes is one of the best ways that you can learn about research in astrophysics in a way that's accessible. So, okay, so to continue, what the study used was this idea known as a general circulation model. These are incredibly common now. What it does is that it simulates what the atmosphere of an exoplanet looks like. So it takes in a bunch of planetary properties and spits out what the atmosphere could look like using the motion. This figure was actually developed at the NASA Goddard Institute for Space Studies for the Proxima Centauri b exoplanet using this global circulation model known as Rocky 3D. But of course they put in assumptions that it's covered with an ocean, it has a modern Earth-like atmosphere, which is why the temperatures are more reasonable. But from that limited information, they were able to simulate what the atmospheres look like. And these are really commonly used, and they rely on PDEs, partial differential equations, which I am actually working on a course now. And they rely on numerical methods. And they require a lot of computational resources, so they're typically run by supercomputing clusters. So okay, so what did this study find, right? What they found was previously, when this system was being analyzed by the Hubble Space Telescope, they thought that it might have these sand-like clouds of minerals because the night side temperature was so low. And specifically these minerals called enstatite and forsterite. And so what this figure in this paper showed is that these data points, which are these black diamonds, are lower than the prediction, which means that WASP 121b actually has a lower night side temperature than predicted by the models, which means that the night side temperature is actually cold enough for mineral clouds to form and to rain crystals of rock. Which is crazy. I mean, that also sounds like a balloon's worst nightmare. I mean, it's that's a crazy thing to think about. So this is one example of modern research that is using these our powerful abilities for simulations to actually trace the atmospheric composition of an exoplanet. Okay, so that's enough yapping, because we just got to the very end. So just to recap, in this presentation, we learned what are exoplanets, what types of exoplanets exist, how do we find exoplanets, how do we identify habitable exoplanets, what future missions will study exoplanets, and what have we found from James Webb. So that being said, thank you all so much for listening. And it's time for some Q&A. Yay! I hope you enjoyed this. I haven't done a live lecture in a long time, so I'm a little bit rusty, but now, while I wait for questions to come in, we actually have quite a few already, and we're also going to have some of the STEMTubers join us on VC as well, voice call. But first, let me check the poll. Looks like 69% of you believe that there is life outside the solar system. 6% of you said that there's no life out there. That's so sad. Well, hopefully this presentation was able to convince you otherwise. And 24% yes in the solar system. Well, for context, I'm of the opinion that there is life in the solar system. Woohoo! Great talk. Thank you so much. This is amazing. Your passion is contagious. Oh, thank you so much. Oh, I feel like these kinds of compliments are really what keeps me going, right? I'm really glad you guys learned something new. I hope the excitement I have for exoplanets is something you guys share too. Okay, so that being said, let's do a quick Q&A, and then I will open the floor, and then I'll connect to voice chat. Here, let me... Boop. So, oh my god. So this question is from Stella. Oh my god. Ah! That's a big question. Oh my god. The presentation was very good. Thanks for the presentation. Oh, thank you guys so much. Okay, I'll make this small. Oh my god. I'll make this smaller, I promise. Okay. How have our methods for detecting exoplanets been refined over the years? And what does the future of exoplanet detection and determining potentially habitable worlds look like? Oop. Hold up. This is glitching out. Okay. So, I mean, it really varies, right? First, we started out with transit methods. That's our most common method. Nowadays, we are also looking at new types of detection, like what I mentioned, gravitational microlensing, even direct imaging as our telescopes have been getting stronger, and even using spectra. And that's how we determine what potentially habitable worlds look like. The spectra give us the ingredients of each exoplanet and tell us what their composition is like. Now, okay, that answers your question. Next up is from the list of super habitable exoplanets, which one do you believe to have the greatest potential to have life in it and why? And this is from Eternal Sonata. I have to say, I'm a little bit bearish when it comes to these exoplanets. There is a list of them on Wikipedia, and actually before this, I was like looking at it. A lot of these planets look really great, but unfortunately, like, they have certain conditions like radiation that make it a little hard to detect. There was one, like Kepler 69c, that I jotted down, but apparently there's a lot of error bars, and it actually might be more like Venus. I'm actually more convinced that, like, Europa has life. Like, I'm very convinced that Europa could have life. Like, it could even be like bacteria in hydrothermal vents. If you guys have ever seen a video of a hydrothermal vent, like, there's like crabs and like lobsters down there in some of the most extreme conditions in Earth. If life can sustain there, then life can sustain in Europa. Okay. Thanks for answering, Coach. I'm going to bed now. Thank you so much for joining. Rip. Looks like I caught the end of this. Actually, we're just doing Q&A right now. So, is there already an ethical code or a proposed one in the case of exoplanets? And this was from PogChamp. I actually also had to Google this one in advance. There was this one article that I read that was from like a conference that was suggesting an ethical code. In general, no. There's actually not that many regulations on space policy in general. So, yeah, no. But who knows? Maybe we will be the ones to actually develop it. I think it would have to... I think there are general ideas of how we would encounter and interact with life forms. Like, for example, with the Golden Record on Voyager, like, we've thought about ways of trying to communicate ideas of science and communicate the diversity of Earth. But when it comes to, like, interacting with aliens to make sure they're not, like, violent, no idea. No idea. I think that's the kind of thing that our Earth is going to figure it out as we go. Hopefully it won't be too weird. Okay, next question. This is by Astral Atropos. I actually chuckled when I read this. If a planet outside the solar system is called an exoplanet, why don't we call the planets in the solar system the endoplanets? Honestly, there is no reason why we shouldn't call them the endoplanets. Maybe we just call them endoplanets from now on. Maybe we start this trend. We are the trendsetters. We are the change we want to see in this world. But it's because, like, we didn't know exoplanets existed. When the word planet was invented, we thought we were the only thing out there. Now, exoplanet suggests that it's outside the solar system, but I guess it's like, it works. We can call them endoplanets. That was such a fun question. Thank you for that question, Astrotropos. Alright, so if you could have a habitable exoplanet if it had an atmosphere so thick it was referring to liquid like a volcanic activity providing heat. This is from Paul Storm Chaser. Let me format this a little bit better so we can read it. Yeah. So if you have an habitable exoplanet if it had an atmosphere so thick it was almost liquid. I mean, I think anything is possible. It could be like that. And I've heard of cases, I mean, there is no life detected on Venus, even although tangentially we did think so, like back in 2014 when we found this chemical compound known as phosphine, but that was later disproved. There are theories that life could exist in the atmospheres of planets. And it's very much possible that an exoplanet could have an atmosphere that it's almost liquid. I mean, we found planets with clouds of quartz, right? We found planets that could have like solid clouds. So yeah, I think anything is possible. Yeah, no, this is kind of freaky. I think the really cool thing about studying exoplanets is that really anything is possible. Alright, so that was the last of the questions in the Google form, which means that with the remaining half hour or so, I'll be right back. I'm going to quickly connect my Discord voice call and see if any of the other VTubers in the STEM Symposium want to join. I'll be right back. Boop. Okay, wait, I'm figuring this out. Okay. All right. Let me make you a little bit better. Okay. Hi, testing.
Hello.
Oh, wait. Okay, let me just make sure that looks like the audio is not working. Oh, I see.
Oh, you have to add the Discord first, probably.
I'm doxing myself. Okay, sorry. I just had like my Discord just like show in the back. Okay. Here, let me make your audio a little bit louder. Okay, testing.
Hello.
Okay, hopefully everybody can hear that. Hopefully the audio is good. How does that sound? Okay, so... Okay, you hear it now? Okay, great. Not that scuffed. Not that scuffed. Here, let me actually increase your audio a little bit more. Oh. I actually decreased it. It's okay. The Z in Syzygy stands for scuff. Okay, cool. Okay, great. Pretty good? Right? Okay, that's good. So okay. This is Dr. Ekelus. Am I saying that right?
Yes.
Okay, great. So, Dr. Ekelus reached out to me to be a part of this STEM Symposium. So, do you want to just introduce yourself first?
Surely. Hello, everyone. My name is Dr. Ekelus. I am the first Brazilian scientist VTuber. I am a graduate in biology and a specialist in human-assisted reproduction.
Woohoo!
And yeah, that's pretty much my introduction. Yeah, so the STEM, the science, the VTuber STEM Symposium actually, it was an idea from Cave, who was one of the original participants, when he was doing his first live stream anniversary, and since then we just continue with the event, and we're having a blast so far.
Yeah, no, that is so cool. I mean, thank you so much for having me and for planning something like this. So, are you primarily on YouTube?
No, I'm primarily now on Twitch. I have to return to YouTube. I was doing some scientific videos. So I'm Brazilian, so my main content is focused on Brazilians. Sure. So
Cool.
I did videos in Portuguese as well. I don't know, just Portuguese actually. And I am trying to do some live streams when I can make like discussion of articles and stuff like that as well.
Wow, no, that's so cool. And I mean, I have to say, like, it's really cool that you're also doing science communication in Portuguese. I mean, that's really cool. Also, I dropped your card link into the chat, so Orbeez, if you haven't already, go subscribe, go like, go everything. Dr. Ekelus is
Thank you very
really,
much.
really cool.
Thank you very, very much.
Yeah, so there's a question in chat asking if your discipline is embryology in particular.
So embryology is my personal formation, but the topics I normally discuss is science in general. So pretty much everything.
Yeah,
If
no,
I
that's
don't know
so
something,
cool.
I go read a lot about it.
Yeah, I mean, I think it's really cool. I mean, there are so many. There's a really good science VTuber community, and I feel like I've been finding more of them, including with Dr. Ekelus. So yeah.
Yes. Oh, yeah. That's the thing. The whole idea of the symposium is to there are many science VTubers, and there are even more now. When I began around 2021, but now there are a lot of us, and the whole idea of the symposium is a way to bring the SciTubers, if I can call us that, kind of together and maybe have us interact with each other as well. Because there is one thing, if I've ever learned in science, is that no one does science alone.
Yeah, no, it's a team effort. And I think especially something like science communication, it's better. I mean, it's more fun when it's a team effort, right?
Exactly.
Yeah. No, that is so cool, though. I mean, thank you so much for reaching out and for finding me, too. And this is a really
Thank you very much
diverse
for
group.
agreeing. Thank you very much for agreeing and to be present in this event. Actually, it's a very good idea when we begin.
The pressure was a little on me, but I hope you guys enjoyed. I hope you enjoyed my exoplanet presentation as well. I know it's probably a little bit different from your main discipline, but I think it comes to show the diversity of STEM tubers that are present in this symposium.
Oh, absolutely. And I love the presentation. It was very, very good. Thank you very much for this.
Oh, thank you so much. Yeah, so I was wondering, like, do you have any questions for me, or maybe we could just talk
I
about
do.
science?
I have actually a few questions. Actually, I had a whole Word document with some questions that I wanted to ask, but your chat was kind of asking them already, and you already answered them. But I have a few yet.
Oh, wow. Oh my god, a whole document? That's crazy. Yeah, no, I mean, feel free to read any questions that weren't answered.
Yes. So, yeah, the first one actually is more of a comment, actually. because there was the in the beginning we kind of discussed a little bit on the possibility of life, and there was a formula, right, for calculating the probability of life. If I'm not very mistaken, the Drake equation.
Ah,
I don't know if you're
yes.
familiar with that.
Yes, the Drake equation. Actually, that's a great point. I did not include that in this presentation. But yes, I mean, I guess it's not directly related with exoplanet data, but it is a really good way of thinking about how many, you're right, the probability, the percentage of planets out there, or the number of planets out there that could potentially host life. So, for those of you who don't know, the Drake equation was made as a way of estimating how many planets in our universe could host life. So it takes in a lot of different factors. I believe it takes in like the number of planets that we've think that are out there in the universe, the percentage of the planets that are in a habitable zone around the star, the percentage of the planets that could host liquid water, the percentage of the planets that could form microbial life, and then furthermore, like the percentage of planets that could form civilizations, and then later, that could communicate with us and be detectable from Earth. And from this, depending on the numbers that you put in, which there's a lot of big uncertainties, you can figure out how many planets would be detectable from Earth or communicatable from Earth. So yeah, that is the idea of the Drake equation. I'm actually so glad you brought that up. It's a really, really cool equation. I definitely recommend checking it out.
Ooh, all right. Yeah. Do you know how I when you were presenting, I saw actually there are many there are many research centers that did those researches. And do you know how many research centers do we have on exoplanets?
Oh wow, I'd say like almost every major institution, probably most institutions that have like astrophysics. Okay, so maybe most astrophysics institutions have studies dedicated to exoplanets. But I think in general, exoplanets is such a team sport. Like you said, science can't be done alone. And I think exoplanets is a really good demonstration of that because, first, these space telescopes are hard to put in space. They require a ton of effort from all sorts of people all around the world. In addition, the data that is generated doesn't just go to like one person. It tends to be like distributed amongst teams or later even publicly distributed for people to look at. And then finally, like exoplanets are so cool because it is one of the fields of astrophysics that has a strong citizen science community. Now, what I mean by that is that ordinary people who may not have gone to school in astrophysics, people who may not be professors or be actively conducting research, can access public exoplanet data. And if you go to the NASA Exoplanet Archive, you can actually access that data for yourself. And you can play around with that data. So I'd say there are thousands of institutions out there that study exoplanets, but obviously there's so many other places, missions, people outside of these institutions that are all dedicated for this search for exoplanets. So I hope that answers your question.
Yeah. It's all a joint effort, really. All of science can be that, actually.
Yeah, no, exactly. And Astrokara in the chat says, I know one of my friends who works on this data and are finding several planet candidates. Yeah, no, exactly. It's so cool that it's publicly accessible. And if it's something that somebody in chat wants to study, I mean, it's all out there available for people to play with.
Okay, so a few more questions.
Mm-hmm.
I have, I believe, just 2 more questions and then 2 points I want to talk about.
Mm-hmm.
Okay, so can the presence of planetary rings affect the exoplanet, the planet's environment? Do you know that?
So I'd say yes and no. Like, for instance, like for Saturn, like because of its distance, because of how it was formed, like it would be a gas giant. But I also say yes because recently we've been finding exomoons, which are moons that orbit exoplanets. So that shows how strong our telescopes are. And in those cases, a ring around a planet is made up of like a bunch of tiny rocks. So typically these rocks are stable enough to stay in the ring. They won't like cause any impacts on the planet itself. But it could affect the moons that are orbiting around it because they have to clear out their path. It could lead to more moons forming. It could lead to more the moons around the planets experiencing collisions. But typically, planets that have these rings tend to be ones that are more massive. Like in our solar system, the planets that have rings are like Jupiter, Saturn, Uranus, Neptune. I'd say that it could make it, I mean, if there was like a spacefaring civilization, it could make it a little harder. But in general, I don't think it impacts the exoplanet itself. But I mean, it's this cool idea that like rings could start to form around exoplanets, similar to what we see in our solar system.
Yeah, makes sense. Makes sense.
Mm-hmm.
Absolutely. Let's see. Oh yeah. Last question.
Mm-hmm.
Yeah, I know AI is kind of a weird topic to discuss in the VTuber community in general, but what about in the exoplanetary research? How is it being used actually?
Yeah,
Because I know in
actually.
my field,
Mm-hmm.
in human reproduction, we are using quite a lot of AI to help us select stuff. So how is it in the exoplanetary field?
Yeah, I think even in astrophysics as a whole, AI has been really important. Even before AI, the idea of machine learning has been important because at the end of the day, machine learning is basically identifying trends in data. And AI is doing that to a way that is more efficient and more powerful. So with exoplanets, there is a ton of data that we're scouring through. There are thousands of exoplanets, thousands of candidates, but more importantly, there's like hundreds of thousands of stars that we've looked at for exoplanets, right? Which then means we have a lot of data to filter through. Now, I can't think of an example off the top of my head where AI has been used directly, but I do know that in general, machine learning and AI techniques have become more integrated. I can speak for on like the galaxy end. In galaxy clusters, there are so many galaxies in there. Using machine learning techniques has been really great to understand these galaxy properties. I think in general, like AI can be a bit of a taboo topic, but when it comes to data analysis, it, like chat suggests, at the end of the day, it's pattern identification extension, right? You are identifying patterns in the data, you are more efficiently scouring through data, and you're trying to find trends in the data to support your conclusions. And I think in that case, exoplanet research, like probably every other field of, okay, that's probably a broad generalization, but exoplanet research, like other data-driven research fields in astrophysics, have benefited from the rise of stronger machine learning and AI techniques.
Yep.
It's really cool how you're using AI in your field as well. Because I would assume with like human data that it might be a little bit harder because I'm worried about the potential like biases that could emerge from using AI on human data.
Well, not so much on human data. We use more it for identifying, for instance, helping us to identify the better sperm cells, for instance. So
Oh, yeah. So
in
that's
a
similar to, yeah.
yeah, it's very similar. It's the same thing about pattern recognition.
Yeah, yeah. Wait, that's
Because
so cool.
yeah,
Yeah.
because I mean, even in the same well, I'm just gonna say because I can't say in any other way about my field, but in the same ejaculate you have a billion number of sperm cells, but the sperm cells not always are the best one. They are some have some faults, or some doesn't have the tail. But so the AI, we have now microscopes with AI technology aggregated that can identify the better ones.
Yeah. So it's like pattern recognition. It's very similar to like how we're filtering through exoplanet data. Wait, this is so cool. I mean, I think AI has sort of benefited in data analysis for fields including yours and for exoplanets, which is this is so cool. I love this connection.
Yes. Okay. I do have, I believe, one more thing I would actually want to talk about.
Hmm.
The thing is about the rogue planets. I thought that was very interesting.
Hmm.
Uh, when you said that there were rogue planets that had oceans, uh, is there? I mean, um, even if those planets have oceans and they have storage to maintain them heated, I do wonder if there is a kind of duration on how long they will keep the heat until those oceans kind of freeze or something like that.
Yeah, rogue planets are probably the least likely to be habitable, in my opinion, because for habitable conditions, you not only need like a solvent like water, you not only need, the ingredients for life, but you also need energy. Like for plants, we need energy for these plants to sustain themselves. We need energy as humans. Even the microscopic organisms at the bottom of the sea get energy from the hydrothermal vents, from the heat of the earth. Which is why rogue planets in general are just less convincing as potential habitable candidates. That being said, there could be leftover heat within these planets, from their formation, from being ejected out of the system, and that energy could heat up a potential ocean that's in a rogue planet. But that in itself is also less likely because when a rogue planet's by itself, there's no energy, though the water will tend to freeze unless it's underneath some sort of thick crust, for instance. So I'd say in general, like, yes, there's a lot of skepticism to be had with rogue planets. They're probably not our best bet to understanding or finding habitable conditions out there in space. And you're right. Over time, if there is any energy in the planet, it would probably dissipate and go away. Which would definitely not be stable. Because for life to develop, it needs stability. It needs conditions to be roughly the same for a long period of time for life to evolve and not die out. And rogue planets are an instance where that is a little less convincing.
Yep, that's right.
Mm-hmm.
Yep, I believe that was it on my side.
Yeah, well, thank you so much for all of the really good questions. Yeah, no, a lot of that was like really, really interesting. And I also love the connection between like, how AI is being used between like astrophysics and biology. It's really, really cool. So, yeah. I think there's also like these in chat. Marlin is discussing about how AI is being used for like anomaly detection. There's this thing called a Waddington landscape. I don't know anything about biology. Okay, that's not true, but like I'm not well versed in biology. But a Waddington landscape by identifying states that cells are more likely to be. But yeah, I mean, at the end of the day, it's just data analysis. Times are changing. I think right now is a really exciting time to be part of these like data heavy research. So yeah. Well, thank you so much for all the kind words and for the questions. I mean, if you have anything else to add, otherwise, I think we'll be wrapping up.
Okay. Just to mention, so this was the first presentation we had in the symposium, and we will have more. Actually, yeah, today. Well, if you are on Brazilian time, it is today. If you are on, I believe it's Eastern time. Eastern time it is tomorrow. I believe that. Yeah, timestamps is a bit confusing for me. Yeah. So we will be continuing with the science symposium later, and it will be on my channel on Twitch and also YouTube. I do believe you have the links. Yes, you do have it.
Yeah, let me
Well,
just
yes, that's it.
Yeah, let me quickly download the schedule just so that I can show it. Once again,
Oh, sure.
thank you so much for making this event possible. And then here, okay, here, let me show that.
Oh, thank you very much for being a part of it.
Yeah.
Your presentation was amazing.
Yeah,
really,
so
really
this
good.
is the full schedule, so I was the first one. It's a lot of big pressure. You said yours was tomorrow?
Yeah, I am not doing a presentation this time. I was more on the organization aspect of it. But yeah, so tomorrow we will have Dr. Toto and Professor Links, and then we will end with Mr. Ages
Yeah,
for
so
all of
yeah.
the VTubers. Scientists.
I have the schedule up here on the screen. So tomorrow we have Dr. Toto and who generously did the raid, thank you so much, and Professor Links, who will be talking about STEM for Life, an adult's guide to learning. So for those of you who are excited to learn, which I hope is all of you guys, that will be tomorrow. And then Mr. Aegis is going to be talking more about psychology, stimulation saturation, how our constant stream of stimulation is stupefying us. So really exciting talks ahead. So yeah. Okay, well, I think that's about it. Thank you all so much for joining. Thank you, Dr. Ekelus, for also joining us on the Discord voice channel. This was an incredible symposium, and please go check out the other STEM VTubers. This is an incredible community that I couldn't be more thankful enough to be a part of. That being said, my next stream will be this Saturday, I think in the morning of PST, so like 10 a.m. PST, which will be a collab with Carbon on space engineering testing. So be ready to learn once again. We are engaging in a whole week, well, 2 weeks of learning. So I hope to see you guys there. And that's it. So thank you all for joining, and I shall see you guys in the next one. And of course, if you like this video, please comment down below so I can actually do more of these. I want to see any questions or comments or support from you guys. And I will hopefully do more of these live lectures soon. Okay. Oh, my voice is going out.
Remember to drink water. Stay hydrated.
Yes! Hydrate or dihydrate. We are not going to be a fried exoplanet. We are going to have water. Okay. I will see you guys in the next one. Bye-bye.
Bye.
Bye-bye. Bye-bye.